So for the first determinant property, I want to think about what happens for the determinant of an inverse of a matrix. So the inverse means that I have A inverse times A. And if I put those together, I get the identity matrix, or the identity operator, the one that does nothing. So if I look at my little unit cube under the identity operator, I get back the unit cube. I multiplied it by a factor of 1, so the determinant of the identity matrix better be 1. So if I take the determinant of all of this, the right side is going to be 1. And I'm going to take the det of A inverse times A. But I'm going to use the multiplicative property of the determinant that I justified for you last time and break this farther down into the determinant of A inverse times the determinant of A. And if I just move det A to the other side, I know that the determinant of the inverse is 1 over the original determinant. So this makes a lot of sense. If the determinant of A grows the volume of the unit cube, then the determinant of A inverse is the opposite of that, and it must shrink the volume. And critically, this clues you in that if the determinant of A equals 0, we can't evaluate this. And the inverse must not exist. So mirroring that kind of thinking, I next want to talk about what happens when we try to take the determinant of a rotation. Well, I'll be a little more general than that, and I will call this an orthogonal transformation, where the rule is that r dagger times r must be equal to the identity operator. Actually, come to think of it, I'm going to make this a little more general than that. I'm going to say that these are unitary and allow for the possibility that these might be complex, and we might be doing some complex conjugating in here. So, mirroring what I did before, I want to take the determinant of each side. So, it's going to factorize just like it did before. So when I dagger, I do two things. I complex conjugate, and I transpose. The complex conjugate can just be pulled out. When I have a determinant, I am multiplying and adding a bunch of things together. And importantly, when I take a complex conjugate, if I have z1 times z2 plus z3, and I star all of that, the determinant is a whole bunch of multiplication and addition. So the star is just going to pull right out the same way it does for multiplication and addition. And there's another property that you'll have to take my word for, that the determinant of a transpose is the same as the original determinant. This is one of those things that's easy to justify but hard to prove. The transpose is just switching rows and columns. It's just switching how you arrange your information. And how you arrange the information shouldn't change the fundamental properties of what happens to the volumes under these kinds of transformations. The volumes are the fundamental thing to the operation. How you arrange the information is more about how humans are organizing this in particular coordinates. So the determinant of our dagger is just going to be, I will pull out the star, but other than that, it's the same determinant as before. And now we branch off into two possibilities. So if R is real, then complex conjugation doesn't do anything. I've got det R squared equals 1. So det R has to be plus or minus 1. Now we can bring in the fact that I've alluded to before about how reflections are lurking in the background here. The rotations are the ones where the det is plus 1. This keeps the orientation. If I have x, y, and z in a certain order, as I rotate these, I'm going to maintain that order and that orientation. But if I have x and then y, and I rotate it, and I reflect it across the x-axis, now it looks like this, and they've changed orientation. If you reflect a human being, the heart is now on the other side. So reflections swap orientation, and they must be the ones where the det is negative 1. On the other hand, if R is complex, that means that I have det R times its complex conjugate. That's going to be absolute value of det R squared is equal to 1. And that means that det R is on the unit circle. And it's going to look like this, which is just like a complex rotation. And that makes a lot of sense. If I'm telling you that these unitary operators that obey this rule, like preserving lengths and preserving angles, and they're doing something like rotations, but it's complex, they should do something like this. Fundamentally, e to the I theta does rotations. So if we take the determinant, if we want just one volume number to characterize what these complex operations are doing, we're not going to be able to fully visualize complex rotations. We just don't have enough spatial degrees of freedom in our brains to do that. But if you say, I'm just going to have one number that characterizes this, and it's e to the I theta, and it's one complex number that does a rotation, yeah, that's what you would have guessed. That's what a complex rotation should do. So there are a few more determinant properties that we've linked to here. I'd like you to try proving those on your own to get more practice with this, and then we'll discuss those in the in-person sessions in Davis.